In a class of mixture separations that I call anti-synergistic kinetic separations, the hierarchy of intra-crystalline diffusivities of gas molecules is opposite to the hierarchy of the adsorption strengths of the gas molecules. And intracrystalline diffusion influences serve to reverse the selectivity such that the more mobile, less strongly adsorbed component is taken up preferentially inside the pores. An important example of such separations is nitrogen removal from natural gas, say methane. Most known adsorbents, indeed all known adsorbents, selectively adsorb methane due to the higher polarizability. But if you look at the cross-section of a nitrogen molecule, you will see that it's a pencil-shaped molecule with a smaller cross-sectional dimension of 3.3 angstrom compared to 3.7 angstrom for methane. By tailoring the pore diameter, say by using barium ETS4, the diffusivity of nitrogen is several orders higher than that of methane. Indeed, methane is virtually excluded from the pores. BA-ETS4 is in commercial operation for nitrogen removal from natural gas. For background to this separation, see several video presentations on my YouTube channel. The theory behind such kinetic separations is described in my paper that will be online in 2024. As detailed in my 2024 paper cited here, and also several video presentations on my YouTube channel that are listed here, the modeling of a fixed bed adsorber for carrying out kinetic separations requires the solution of partial differential equations for each of the components, and this is the differential equation where C sub I is the molar concentration of gas component I at any time t and position z. V is the interstitial gas velocity. Z is the distance coordinate along the fixed bed. Epsilon is the bed voidage. T is the time. Q with a super bar is the average component loading at position Z and at time t. This is the integral average of the component loadings within each particle at any position Z and at any time t. Indeed, the determination of the partial derivative of the average loading within the crystal is the focus of this presentation. In order to determine the average loading of each of the gas molecules at any position Z in the fixed bed adsorber at time t, we need to solve the differential equation describing the transient uptake of the gas molecules within the crystallites. As detailed in several video presentations, we set up the differential equations for transient uptake in terms of the fluxes Ni, and the fluxes Ni for each of the components is described by the Maxwell-Stefan diffusion formulation, where D sub I is the intra-crystalline Maxwell-Stefan diffusivity of component I, and mu I is the chemical potential gradient. As stressed in several of my video presentations, for kinetic separations, it is essential to adopt the Maxwell-Stefan formulation. Otherwise, the essential features of kinetic separations are not properly captured. The solution to the partial differential equations describing transient uptake allows us to determine the average component loadings at any position z and time t. This information is then combined with the differential equations describing the variations of concentration along the fixed bed adsorber to simulate transient breakthroughs and productivities of kinetic separations. All of the details are provided in my 2024 paper and several other previous publications that are listed in these video presentations. Rather than solve the partial differential equation describing transient uptake within the crystallites using the Maxwell-Stefan diffusion equations, most commercial software, such as those marketed by ASPEN, ProSim, and others, adopt the so-called LDF approximation, where LDF stands for linear driving force. This approximation was suggested by Glueckauf in the classic 1955 paper cited here. Essentially, the time derivative of the component loading, average component loading, is assumed to be equal to the derivative of the equilibrated component loading, and this equilibrated component loading is in equilibrium with the bulk gas mixture at that position in the fixed bed adsorber. In the derivation of the Glueckauf approximation, it is assumed that the parameter d sub I divided by the square of the radius of the crystallite times the time t is greater than 0.1. Or the square root of this term here, which is the product of the diffusional time constant and the contact time t, is greater than 0.32. If we make this assumption, then as did Glueckauf, we can relate the time derivative of the averaged component loadings at any position z as given by this simplified expression that obviates the need to solve the partial differential equations describing the transient uptake within the particle. The limitations of the Glueckauf approximation are described in detail in my 2018 paper in Separation and Purification Technology. Watch also my video presentation on transient uptake of binary mixtures. So the question I ask here is this Glueckauf approximation good enough for kinetic separations? In this slide, I compare experimental data of transient uptake of binary mixtures in 3 different adsorbents. First is a mixture of carbon dioxide and ethane in DDR zeolite, mixture of normal hexane and 2-methylpentane in MFI zeolite, a mixture of nitrogen and methane in LTA4A zeolite. The experimental data on transient uptake for the more mobile component in each of the 3 cases shows a pronounced overshoot in the component loading as it equilibrates within the crystallite. This is for CO2. There is a maximum in the component loading or an overshoot. There's an overshoot for normal hexane and there's an overshoot for nitrogen in this case. This overshoot happens because CO2 is the more mobile component here. Normal hexane is the more mobile component in this example here. Nitrogen is the more mobile component here. But the more mobile component in here is less strongly adsorbed than ethane. Also in this case, the more mobile component is less strongly absorbed than methane. In this case, however, the more mobile component is also the more strongly adsorbed component, and this separation is termed as synergistic kinetic separation. The dashed lines are the simulations of transient uptake using the LDF model of Glueckauf. The LDF model fails to capture the overshoots, and the overshoots can only be captured by the Maxwell-Stefan diffusion equations. Another point to note is that I show here the requirements of the LDF model, which mandates that the square root of the product of the diffusional time constant times the contact time should be greater than 0.32. And we will note that the overshoot occurs at times smaller than that dictated by the LDF mandate. In this paper that is not yet online, I argue that for kinetic separations to be effective, we need to operate at conditions wherein the diffusional time constants multiplied by the contact time in the fixed bed adsorber is smaller than 0.1. Indeed, it is vital for kinetic separations to nullify the mandate of Glueckauf. In other words, LDF model will never work for kinetic separations. And all of that will be presented in this paper, and when it's available online, I will prepare a more detailed explanation as to why you should expect the LDF model to fail miserably for describing kinetic separations. So I leave the presentation at this point, and you may consider this video as a teaser.